This meeting is being recorded.
Recording.
So, good afternoon, everyone. Let us now move on the final presentation of this afternoon. It's a pleasure and honor for me to introduce Marcia Federson, full professor at the Institute of Mathematical and Computer Science, ICMC, at the University of São Paulo in São Carlos. Professor Marcia Federson is the leader of the research group in the differential equations, dynamical systems, and non-absolute integration at ICMC, and associated editor of the journal Differential Equation and Applications. Among the various activities undertaken by Professor Marcia Federson, I would like to highlight her role as a pro-reitora or vice chair, I don't know how to translate, of the graduate program at Brazilian Mathematical Society, SBM, and as a member of the ENAMA Council, the National Meeting of Mathematical Analysis and Application. I would like to thank Professor Federson for accepting the invitation to participate in this event, where she will talk about stability for generalized stochastic equations. So, Marcia, the stage is yours. Thank you very much for being here.
It's super nice to be here. I have you and also Professor Juan as very important friends to me. You are really serious persons and those friends that you can rely on forever. So it's really a great honor for me to be here and to share a little bit of what I have been doing lately. Mm-hmm. Well, and I'm going to tell you about these some results of this paper with Professor Fernanda Andrade da Silva and Everaldo Bonotto. Everaldo Bonotto is from the Department of Applied Mathematics here in São Carlos, and Fernanda was my PhD student, and now she is his postdoc student. So we are doing things together. This is the paper I'm talking about, and so these are really fresh results. And the aim of the talk is, in the first place, to let you know how to put stochastic differential equations into a larger class of equations, which is going to take into account a special type of integration that came to Brazil with Professor Stefan Schwabig when he was invited by Professor Scheinhonig to spend half a year in São Paulo. And I believe that we have been the only ones here in Brazil doing this kind of non-absolute integration. And then I'm going to highlight some issues in stability results. So as we have the time going, since I was in my PhD earlier, since I was, because Chaim was my master advisor, my master degree advisor. And I learned these integrals, these non-absolute integrals with him. And lately, when I came to São Carlos, Plácido Tabas was my postdoc advisor. And he allowed me to continue doing these things. But Plácido is a guy from equations with delay. So I was trying to manage both things together so that we could do things together. So lately, I came to understand that abstract ODEs could be, if you take an ODE and look at it in its integral form, and the integral is a different integral, then sometimes you can relax the assumptions on the right-hand sides of the equations, and this was important for me to do. So generalized ODEs, now we know that it encompass many types of equations, as equations with delay and impulses, and dynamic equations on time scales, integral equations, and some PDEs. So then I was thinking, what about stochastic equations? Can I do the same? Can we generate a space and then put everything inside? And so we have been working on this, and the answer is yes. So just for you to have in mind, this here is on the left is Henstock, on the right is Kurzweil, and they have met, and they used to do the integration, this integration theory separately, but it was at the same time. So this is why the integral got the name of both together. So the main feature of this integration theory is that it integrates highly oscillating functions, which are not absolute integrable. So this is the main difference. So Lebesgue integration, you can do a parallel with absolute integration because a function is Lebesgue integrable if and only if its norm order, its absolute value, depends on the counter domain, is also integrable. But here we cannot do this because we are dealing with functions which are not of bounded variation. So we cannot put the norm inside the integral because then it explodes. So we have many typical examples of functions which are not integrable in the Lebesgue sense, but are in our sense. This one, for instance. By the way, this one is Riemann improper integrable. So one could say, oh, you're managing to escape somehow and doing improper integration. I agree. The nice thing on Kurzweil-Henstock integration is that these improper integrals, they do not exist, because when you try to enlarge the space of integrals to a bigger space, then it exists. It is exactly the same. You in the end is not getting more integrable functions. These, we say that the Kurzweil-Henstock integral is invariant under Cauchy extensions. Okay, so here is another example. The purple one is a horrible oscillating function. And these oscillating functions, and then we know that particularly Brownian motions are coming from Robert Brown, and this is the flower that he was studying, the pollen coming from it. So particles in a fluid are one applications of the applications of Brownian motions. And for Brownian motions, we know that the particle is of unbounded variation. So we also have this year 1905. This is a very nice year, and it's called Annus Mirabilis, because in this year, Einstein published 4 awesome, magnificent papers in super different things. So I think he's really a genius on the photoelectric effect, Brownian motion, special relativity, and the mass energy equivalence, then relating to special relativity. And in this paper in Annales de Physique, he wrote the following: it's possible that the motions to be described here are identical to the so-called Brownian molecular motion. However, the data available to me on the latter are so imprecise that I could not form a judgment on the question. And in fact, when we have that famous experiment, which is called the two-slit experiment, when you send particles to two slits and in a barrier, you see what's going on. For big particles, you have two marks on the wall, the final wall. But for waves, you have a different pattern. And then the interesting and awkward thing that was happening with this experiment in the late 1800s was that for little particles like photons or electrons, you would have the behavior of waves. This is why they were physicians were saying that this behavior is called wave particle behavior, or that the small particles have this dual behavior, this duality. So we have a progress in the study of equations which were dealing with particles in a fluid. So we have these years, and we have the Langevin equation, and then the Fokker-Planck, and then the Feynman-Katz formula, which is the wave function for the Schrödinger equation, the solution itself for the Schrödinger equation, which applies also to Black-Scholes models. So you can see that we were evolving in the difficulty of the equation. So if I take a Fokker-Planck equation like this one, it's known that we can transform it into a stochastic differential equation, like this one, for instance. So here, W is a Wiener process or Brownian motion. For our notation, I would like to talk about this space, which is the space of Hilbert-Smith operators. And in this space, I use this norm here, which resembles us of the norm in small L2. Okay, I would like to have a probability space and a filtration here. This is going to be called a filtering probability space. And what else? I'm working in separable Hilbert space. So U and V are separable Hilbert spaces. And the difference here with a normal Brownian motion is this thing here, this Q here. When this Q is a covariance operator, then normally we ask these to have mean 0 and variance S minus T. But here, because we want to deal with these Q Brownian motions, which are very much related to Hilbert-Smith operators, then we put this Q here. But the rest is almost the same thing, the same requirements for a process to be a Brownian motion. We will use the letter capital L for the space of random variables with this norm. And we will use the round L for stochastic processes like this. So this big X here is a collection of random variables. One of these xt is here. And the collection of these xt is in this round L2 here. And the norm of this L2 involves the expectation E. So these are coming from the classic theory of stochastic equations. And the idea now is to define an integral and see what's going on. Ito's integral has in mind the idea of Lebesgue, where Ito wants to consider a sequence of, say, elementary functions. The way we do Lebesgue integration is similar when we deal with this Ito integration. So for those used to Lebesgue integration, it's not difficult to study Ito integration. And some guys from Singapore, descendant from Henstock, decided to study what would be this non-absolute integration in terms of stochastic processes. And then one has to have these intervals. One could ask me, can it be closed here? Yes, it can. It's just that we are used to put it open here and closed on the other side, but it can be closed in both sides, in both ends. This UI here is therefore the mark to the left. This is why we called such partition belated partition. For the Cauchy integral, on its very original definition, he used belated partitions. And we are going to require that this partition is delta fine, meaning that these intervals have to be inside this other interval, and this delta here is a function, is a positive function of the interval. Okay, so now this is not enough for us to get the partition of the domain for the version of stochastic processes and Henstock-Kurzweil integration type of doing it. In the beginning, they thought this was enough, but then people realized that one should need to have this other number here, which comes from the Vitali covering lemma, where you have this number that is guaranteed by that lemma, that the interval minus the sum of the measures of all these subintervals is less than this eta. So in order to guarantee that for every delta eta given delta function and eta number, we have such partition, we need to deal with both of them and not only with delta, which would be maybe the intuitive way of thinking for me, for instance. So we need to have here a phi-adapted stochastic process, as usual in the stochastic theory, that if T1 is bigger than T0, then the set of processes in T1 contains the set of processes or times in T0. Okay, now we are going to define what would be the Ito-Henstock integral. This is known already, and it is mainly developed by the guys from Singapore. So I would say that a stochastic process F is Ito-Henstock integrable with respect to a Brownian motion B. If for every epsilon, I can find a function and a number here such that for any delta eta fine belated partial division like this, the sum, this is a Riemann sum, Riemann type sum, converges to a number, or we'll say it's not a number necessarily, it can be a guy from the space of the contradomain, the Hilbert-Smith operators, or V or whatever. Here it would be in V. We want the expectation of this difference in norm to be small enough. What is the idea here? Usually, for the deterministic case, we want the Riemann sum to get to a limit. That's the idea. Because we are dealing with a stochastic process, it's super natural to think of the expectation of this approximation. So we have the very much same ideas, but because we're dealing with a stochastic process, we put expectation in our things and the same ideas work. So in the end, if you have Ito integrability, which is born naturally in this space here of stochastic processes, then one can prove that you have Ito-Henstock integrability. But because of the Ito-isometry for the Ito-Henstock integral, we have the converse. So these two integrals happen to be the same. Okay, but now, still thinking of a generalized space of equations where I can manage to put not only stochastic process, but also impulses and delays and timescales and so on and so on. In the framework of stochastic process, I would like to define what would be the analog of generalized ODEs now for this stochastic process. So I would have to define as something similar to Kurzweil's integral, which is the following. We have here a Riemann sum of a function h, and this function h is a function of points and intervals. But this is, after all, the idea that we have in mind. We always, for the partitions of the domain, we always do this kind of thing. We are dealing with subintervals, and then in the subintervals, we consider a point which may be in the interval, in the subinterval, or close to it. Okay, so having the same idea from the Kurzweil integral, which generates generalized ODEs, it's just a matter of putting this expectation here that we have the same thing for stochastic processes. Okay, so now our function of a point and an interval, we can think of it in the following way. Suppose you have this interval here and a point which is close to it. It can be an endpoint, it can be inside the interval, or it can be very close to the interval. And think now of changing the function h by a function g of points, this difference of g, but g is only a function of two coordinates of points. So we can rewrite these, and we'll rewrite the terminology of the integral here, like this, okay? We don't put here any ds or dτ or d whatever, because we are already used to the Riemann-Stutis sum coming into this definition. So the Stutis part is already inside, so we don't need to specify ds or dτ or d whatever. In the end, we know that a sum of this h can be rewritten in this form or in this form. So in our notation, this is precisely this stochastic, but Stutis also type of integral, where the b is the Brownian motion. Okay, so we think of this integral form here, and for stochastic processes, one would say that if you have a stochastic process whose random variables satisfied such an integral form, then you are speaking of a mild solution of the stochastic process with d, dw, d, whatever. In the end, in the theory of stochastic processes, they deal with the integral form. So this is what we are doing here also. Specifically, if we have these stochastic processes here, then the integral form is given in this way, and we can say that a stochastic process whose random variables satisfy this equation is a solution of equation 2. One could say a mild solution, one could say a Ito-Henstock solution, or something like this, because the integral is in terms of the Ito or Ito-Henstock integral. So then we have this result that relates the solution of a stochastic differential equation and our generalized stochastic equation. If we take for our stochastic differential equation a big F, which is the integrand of the integral, like the integrals of these two parts of the stochastic equation. Let's come back. We are going to integrate here, and integrate here, getting this here. And it's just a matter of changing which integral am I considering now. But the idea is all the same. The idea is all the same. Okay, so now we have conditions for later existence and uniqueness of a local solution. And we define this space of right-hand sides of the stochastic, the generalized stochastic equation. And we require the following two conditions in dots here. And I want you to pay attention that here, if you don't think of this E, pretend this E does not exist. You have here a type of Kara-Theodoric condition, but concerning the integral. And here you have a type of Lipschitz, more relaxed Lipschitz condition, but again on the integral, because if you require these classic conditions of theory of differential equations on the integral and not on the integrand itself, you can have bad integrands, and yet the integral will be good. But because we are dealing with stochastic processes, I'm going to put expectation here. So you see that we are coming from deterministic equations, but we carry the ideas and put them here, just learn how things work here, and we can just see that the same idea applies. Okay, so existence and uniqueness of a solution of this generalized stochastic equation is guaranteed. I say generalized stochastic equations because the usual stochastic equation is a particular case of this one. So for instance, let's take this one, this stochastic differential equation, and in particular, the Fokker-Planck equation, which we saw that can be modeled as a stochastic equation. Let's put some impulses. Then we have this Fokker-Planck equation with impulses, and under our conditions, we have a solution given in this way, and we guarantee that this solution exists with this integral here being in the sense of Ito or Ito-Henstock, and this being kind of a random integral, or you could say as a particular case of Ito or Ito-Henstock integral. Okay, so for us to have the uniqueness and existence of solution, it's just a matter of requiring the Carré-Theodori and Lipschitz type conditions on these integrals. So this is what we are doing. And okay, now let's get to it again. And we want to talk about stability of solutions, mainly of the trivial solutions. For us to have a trivial solution, we are requiring that f0t equals 0 for every t. Then we have the notion of a solution, which is a stochastic process, being mean square stable. Someone is writing together with me. If for every epsilon there exists a delta such that having the initial condition, this should be x index A, small enough that the expectation of the random variables would be small enough. And in particular, if we add the condition that the limit of the expectation for t going to infinity equals to 0, then we have asymptotically mean square stability. So our results on the generalized stochastic equations would require some canonical conditions on a Lyapunov type functional, but involving expectation as expected. And then we have these results saying that the trivial solution is asymptotically mean square stable. And as an application, we consider the Ornstein-Uhlenbeck process, and then we integrated it, consider its integral form with right-hand side given in this way, and we proved that under the previous conditions, this process is asymptotically mean square stable. So I wanted you to have an idea that stochastic processes are not a monster. These are okay. it's hard to understand when you're changing a little bit your direction of investigation, but we can do it. And these are other references related to the topic. In particular, this book here is a very, very good book for stochastic equations in infinite dimensions. I love it. And these other papers are from the guys from Singapore. And I would like to thank you very much for this opportunity again.
Thank you, Marcia, Professor Federson. And we now we are open for questions. And I think Juan will open the audio for the people if they want to speak, or you can write in the chat. Do you have questions? Oh, okay. I think no. Um, um, okay. Okay. Marcia, I have a curiosity. You say now at the end of your presentation about this very nice, very difficult presentation for me. For example, this area stochastic. For example, my area in the numerical methods, we have this stochastic equations, no, to solve, and it's not easy, no. We have to use special methods to solve, né? And my curiosity is about for when you introduce these ideas in your courses, in your graduate courses, no? I think you give classes for this subject during in ICMC.
For the stochastic process, only for PhD students, because I think it's a little bit complicated for undergraduate students to understand.
You use some, for example, the knowledge that they have to background, they have to understand. So it's some courses to prepare to attend your classes. So, for example, if one of us want to go to attend a course in the stochastic process, what do you advise? What are your advice about this?
Well, I'm going to say here something that is complicated, because many books on stochastic processes, they are for me not easy to understand. So I have always a very hard time understanding the notation and so on and so on. So when we wrote the first article on the subject, my main concern was, what is the domain? What is the counter domain? This is such a basic thing, but I was always, where am I, the space I'm leaving, where am I going to? This was really complicated. So I believe that we have to look for good books. They are not many. This one from Giuseppe da Prato is one that I like, but it's not for beginners. So I believe that we in Brazil would have to produce more literature in Portuguese, or basic literature, even if we think we are saying a very, say, stupid thing because everyone knows. But but I don't think this is real because sometimes I have so much difficulty understanding. So I was really feeling this solidarity to other people. How can students understand these things if I'm not understanding? Of course, after I got the main ideas, I realized it's more or less the same, but I'm just using expectation here. But you see, for me to get into that, it was not an easy task. So when I talk about it, I try to get people just go and think of what you know about classical Ds, no matter which type of differential equation. What you know from that is going to guide you. Because I believe that we as analysts, we write in a good way. But for stochastic processes, I think we have still some issues. Yeah, so this is my point of view.
Okay.
I have one
It's
question
nice.
you shut.
Yes, I see. We have a question for Professor Elma Mazut. The guy that I was writing with you, I think. The integral here. Can you see? Okay.
Yes.
Go ahead.
The integral here is a generalization of this Tutus integral, or it's a particular case? Is a generalization. This one that I am calling Kurzweil-belated. The other one, the Ito-Hastock, it already exists, and it is precisely the Ito integral. They are precisely the same, but Ito comes with ideas based on Lebesgue integration, and Ito-Hastock comes from another point of view with gauges or calibers for you to cut the domain. So it's interesting to know both sides because for me, I think it's easier to deal with Riemann sums. Because in SDs, non-critical point theory, maximum principal attack. For PDEs, you see what I'm doing here. Okay, for PDEs, I'm not from PDEs. I'm from ordinary differential equations, the equations with delay, which are functional differential equations. So you see, when I put the Langevin and the Fokker-Planck equation, I always looking for the stochastic version of it, so that I can come with results and then go back and say, okay, so for the Fokker-Planck equation, I have this and this and this, but I'm not working with PDEs because I don't know PDEs.
Okay, thank you for the questions, and Marcia for being here, and it's very nice to hear your talks. Very, you talk so well about the so difficult subject, and I think we enjoyed so much.
Thank you.
So, Juan,